This is a production of Cornell University.
Okay, so this whole lecture, I've lectured based on the premise of mapping, but this lecture has all been about how these soils are distributed across the landscape. Okay, and that distribution is controlled by these factors in these processes. Okay, well, let's take a look at some of those things in the landscape that control this distribution. And the classic one is slope. And we call this the generalized landscape position. But if you think about how water is going to move in this, or gravity is going to work in this, you can basically take a look at these different positions in the landscape, and you can predict different characteristics. Do you guys remember when I did that sort of slope? It looked something like this. And it was about depth of soil, and it looked like this. And we had something that looked like this. And then I had actual rainfall versus effective rainfall. There it is. You can make predictions about what's going to happen just by looking at the landscape. Okay, so let's take a look at the landscape. This is classic model. Basically, you're looking at the top. You're basically looking at the summit. You start moving into here. You're looking at the shoulder. Basically, we're basically using our body as the design. A shoulder, 4 is the back slope. You get down into 5s and 6s. You're starting to talk at the foot slope. And then you get down here, and you're in the toe slope. Basically, your body. Okay, so think about how your body, the head, the summit, the shoulder, and basically the form of your body represents the form of the landscape. The head, the summit, the shoulder, the back, the foot, the toe. Make sense? Okay, now think about this model, and think about gravity, and think about that consociation that we just talked about. This one, or not consociation, the association we just talked about. Do you see the relationships? Kind of cool. So then I can go out to the real world. I know what this looks like. I can predict that. Pretty neat. Kind of ish. I'm only getting a few blank stares right now. So, okay. All right. So let's take a look at some of the other features that we look at. Slope is an obvious one. When you go out there, you start climbing that hill, you know it's steep. Okay? So there are other features that we can look at that basically can help us predict characteristics along the landscape. Okay? Some of them are not so obvious. Drainage classes. Okay. Drainage classes. What is drainage classes? It's basically the measure of where the water is in the soil, but more importantly, how easily that position on the landscape is going to drain. Okay, if I have a rain event, how quickly is that water going to either move into the soil or move off the soil? Does that make sense? Okay, so let's take a look. It doesn't rain all the time, and there's not water there all the time. So let's look at some features that we can use to basically predict what's happening with the water. Okay, we have a number of soils here. This is a well-drained soil all the way over to a poorly drained soil. Okay, what are the features? We're basically looking at drainage features. We call them modeling or redox features. And we can predict how the water is behaving based on how iron is moving in the soil or how it's reacting in the soil. You guys heard me talk about this in lecture before, as well as in lab. But what happens to iron when it is reduced? Okay, we have iron. You guys know what it is, right? I put it under water, and I take the oxygen out of the system. Okay. What's going to happen to that iron? It becomes mobile. It becomes reduced. Why? If I take oxygen out of the system, the microbial population that's in that system is still going to want to survive. And if it has the ability to use alternate electron acceptors other than oxygen, it's going to use those alternate electron acceptors for respiration. Iron happens to be one of those elements that they can use. If they use it, they basically take the electron, or they transfer an electron to the iron and reduce it. Now, interestingly enough, when that iron gets reduced, it becomes mobile in water, and it changes color. It goes from the reds that we typically think of as iron to the bluish greens. Okay? Now, I can use those colors to look at water movement. Okay, I'm really not that concerned about the iron, but I can use the iron to tell me what's happening with the water. In a well-drained system, the soil never gets saturated. If it never gets saturated, the iron is never going to get reduced because the microbes in that population, in that soil, don't need to use iron as an electron acceptor. Right? Does that make sense? And I can see that in my soil. I don't have movement of colors. I don't have greens. I don't have spots of red. Okay? As that water table starts moving up, the soil becomes more perched in that system. They get more saturated system. That water starts moving up here. Down here, where the system is always wet, what kind of colors do I think I'm going to find? There's two distinct groups of colors. Let's talk about the irons first. Okay? If this system is always wet, what color is iron? Bluish green, right? If I start seeing lots of bluish greens, I know I have long periods of time where this soil is saturated. Okay? Now, just above this, you see this zone that we call mottled. This is a flux zone. It gets wet and dry, wet and dry, wet and dry. So some periods of the time, that iron is going to get reduced. And it's going to move with the water. Remember, reduced iron is soluble. So wherever the water moves, that iron is going to be moving with it. The interesting thing, though, is the minute that water gets into an aerobic area, without any microbes, simple chemical reaction, that iron is going to oxidize. It oxidizes, it's going to stop moving, and it's going to change color. And the color it's going to change to is red. So if I have a system that's doing this a lot, I'm going to have iron moving up and down a lot. And the minute that iron gets touched by oxygen, it's going to turn red. And so as a result, I have like leopard spotting in here. Above it, looks just like over here. I don't have any saturated periods in here. So basically, my groundwater is going from here to here. You keep this system up. Ultimately, the water table is going to go higher. Basically, the same story here as here, except in this case, the groundwater is fluctuating here versus here. Sooner or later, I'm going to get farther down in the landscape, down in those toe slopes, where the water is basically going all the way to the surface for long periods of time. Wetlands. Okay? In those types of situations, I basically have grays, in some cases, all the way to the surface. Okay? I'll have some potential modeling, but you'll notice in some cases I don't have any modeling. And then at the very top, I'm going to get very dark horizons. Nothing to do with iron. What's going on? Accumulation of organic matter. Okay? So here's my drainage classes. Now, depending upon where in the country you are, these drainage classes can move. But around here, if you have redox features, that's these features, redox features, this kind of stuff. If you have redox features and they are present between 0 and 6 inches of the surface, you have a very poorly drained soil. It's just the way it is around here. It's a wet environment. Okay? Start moving down, 6 to 12, 12 to 20, 20 to 32, 32 to 42, 42 to 52, 52 plus, you start getting into excessively well-drained soils. This is where you start finding those modeling features, those water features. We don't necessarily get out there when it's wet. But if it's been wet for some period of time, you're going to find these modeling features. And you can use the modeling features to tell you where the water's been or where it will be again. Question?
Is that like a sand dune?
It could be around here. It could be a sand dune. Now, it's important to note, this is the drainage classes for around here. As you get out farther west, because these also have interpretation impacts, okay, if you get farther west out west, these poorly drained features are going to get deeper because of their interpretations. Okay, interpretations are not New York, are not New York, are not New York. I mean, if you go to Arizona or the West Coast or the Northeast or the Southeast, interpretations are going to change because you're interested in different types of crops and different type of management issues. Does that make sense? Okay, good, go.
About the inches, is that how far the spotting goes down?
Yeah, so if I find my spotting between 32 and 42, or by modeling, it's a well-drained soil. If it's between the surface and 6 inches, it's a very poorly drained soil. If I don't see it, it's excessively well drained. Okay? All right, we've sort of talked about these, and we'll come back on this. But I wanted to give you guys, go ahead.
If you see like a puddle, if you're walking down the street and you see a puddle, does that mean it's not that like when it rained, the water didn't drain all the way? Is it that the groundwater is like?
Could be groundwater coming up. It should be also noted that for these features, for these modeling features to be produced, this is not a day event. This is consistently been happening over seasons and years. Yeah, a day event, you'll get some iron reduction. But if I just have a couple, individual atom doing this, it's not going to be a big thing. I need to have lots of this to be so that I can actually see it.
They're like tide markers, right?
They're like tide markers. If I have a flood, okay, think of the bottomlands in the south. Right now with all the hurricanes, the water table comes up pretty high and things float, right? Well, when you start seeing cars stuck in trees 20 feet up, this is not like Godzilla's walking around planting, screwing with us. This is the water has basically floated something up and has left it in the trees. Okay, this is a significant event. Okay, if I see this over large expanse of my soil unit, I know that this is a moderately drained soil because I'm finding it here consistently. Does that make sense? So let's take a look at some of these. I'm going to skip ahead, but let's actually take a look at some of these features. And I think we're going to have to kill. Could we kill a couple more light spans up there? Or turn them off, I should say. Can you guys start seeing that? How's that? OK, good. Cool. Al, can you still see us in the back? All right, cool. All right, so these are organic accumulations. Now, this is a jello soil right here, so you can see the ice that's down here. But you can see these organic matter accumulations. Okay? But when we're talking about these sort of water accumulations, notice this one. You see the gray colors in here? These gray colors, that's the reduced iron. The iron has been reduced. But you'll notice at the top, nice dark rich black almost. And that's the organic matter accumulation. Okay, so I have two sort of clues as to saying that this is wet, a hydric soil. This is a wet soil. First, I've got organic matter that's not decomposing. And second, I've got gray colors below, which totally tells me that iron has been reduced. And the only way that for that to happen is the oxygen to move out of the system. And in our planetary system, that means water's in there. Does that make sense? Okay, so here's some of those gray features. You can see this gray feature right here, almost all the way to the surface. You can see these gray features. They come in a variety of different colors. Blue, greens basically indicate that the iron is still there. Stripped out grays, basically the iron's been lost totally. Even the reduced iron has basically been moved to the system, moved out of the system. Then you get into sort of these. Here's that organic rich stuff up here. But you start seeing these reddish spots in here. This is a flux zone. Okay. Yes, the water's coming up here, but for some period of time, this is a dry zone. Because for me to get that red, I need to have oxygen. Okay, because I need to have that rust form. Okay. So it gives you an idea about where these fluxes are, these water table fluxes are. Here, the water is pretty far up there. But you can see there's small patches of red. In this one, it's up here a lot, most of the time. Here's some redox concentrations. I sort of introduced that here with this one right in this picture right here. But let's start talking a little bit more about these. We're going to talk a lot about these in lab as well. But you start seeing these red masses in here. Okay, so we have the oxidation features. Oh, I forgot to say this. Redox. Term redox. Redox comes from reduction oxidation. Redox. Okay, sorry, that was a jargon thing. I apologize. Okay, so here are these redox features. Here's the oxidation features, these red redox concentrations. Here they become a little bit more apparent. In fact, I think the last slide was better. This side a little bit better. You can really see those reds popping out there. And to give you an idea of scale in some cases, some of these redox features can be within the same aggregate. Okay, so there's the penny to give you scale. We've broken this up. I pulled this from the web someplace, and I have no idea where. But basically, you're looking at the edges here. Okay, the interior is gray. The exterior edge, we're seeing red. So what does that give you an idea about what's happening here? Water's moving into the system. It's getting inside these PEDs. The water's staying there. But then when the system dries out, the edges dry out first. And then the water from the interior starts migrating out. Okay, if the water in the interior starts migrating out, it's going to be bringing the iron with it, right? And if it's bringing it out to the drying front, that drying front has oxygen. That drying front, that reduced iron is going to hit that oxygen, and it's going to oxidize. And so as a result, we have these rimes, these rims of red. Go.
This has been a production of Cornell University. On the web at cornell.edu.